faithfully delivering value, exploring great books worldwide. Hi, this is Sally's Book Club. Today we're discussing the book Mathematics as Conversation, subtitled Everyone Has a Math Gene. Math is as Simple as Chatting. The book explores the relationship between mathematics and linguistics, as suggested by the title. These two seemingly unrelated disciplines actually share fundamental similarities. If humans have innate language abilities, could mathematical abilities also be hardwired? Does everyone possess a math gene? Why are some people math challenged while others are math prodigies? Author Devlin believes math should be as natural as conversation. Problem-solving techniques aren't the ultimate goal of learning mathematics. What we need is to think like mathematicians, whether you love math, hate it, or feel intimidated by it. This book is essential reading for you. Author Keith Devlin is a senior researcher at Stanford University's Center for the Study of Language and Information. His research focuses on making mathematics accessible through various media. He has authored over 30 books, including The Millennium Problems, The Math Instinct, and Life by the Numbers. Devlin also hosts NPR's math education program and maintains a monthly blog. In his blog, even bicycles, tires, and U.S. elections become math discussion topics. The 250,000-word book follows natural problem-solving thought processes in its structure. I'll follow the author's framework to explore the math-linguistics relationship in 3 parts. So, Part 1, what is mathematics? What do mathematicians think about? Part 2, what is language? How does language ability develop? Part 3, what's the connection between mathematics and conversation? Let's begin with Part 1. Let's start by considering, what does mathematics look like to most people? So, is it just incomprehensible formulas from textbooks? Sentences that make no sense when heard? Take this example from Chapter 1, Problem 12. Prove that the real part of z is greater than 0 if and only if the modulus of 1 minus z divided by 1 plus z is less than 1, sometimes followed by unpronounceable expressions. Feeling anxious already? Mathematics seems so unreasonable, yet there exists a group utterly captivated by it, mathematicians. Given the chance, they might indulge in it endlessly, like Archimedes, who kept working on geometric problems during Syracuse's invasion, ultimately killed by Roman soldiers. Many anecdotes showcase mathematical genius: Gauss and arithmetic sequences, Euler's 7 bridges, Fermat's last theorem, biographical films like A Beautiful Mind, The Imitation Game, and The Man Who Knew Infinity popularized Nash, Turing, and Ramanujan. When discussing Ramanujan, people often imagine him conversing with formulas. Not literally true, but not pure fiction either. In reality, Ramanujan didn't chat with numbers, but could instantly recognize their properties, like we recognize friends' faces. For example, when hearing 1729, Ramanujan immediately recognized it as the smallest number expressible as 2 cubes in 2 different ways: 12 cubed plus 1 cubed and 9 cubed plus 10 cubed. This came as naturally as noticing names Zhang Duming and Zheng Xiaoming might be brothers. Do mathematicians treat math as common sense? Then why does mathematics feel inaccessible to most? The author argues the gap between math and daily life exists, but not in the way people think. The author uses a house metaphor to describe mathematical thinking. Mathematicians construct abstract mental houses when tackling problems, initially creating blueprints, familiarizing layouts, selecting furniture. Once built, blueprints become unnecessary. Focus shifts to furnishing, understanding, and living in it, solving problems. Thus, when facing math problems, our first task is building this mental house. Entry isn't easy. This house is constructed from abstract mathematical objects bound by logical structures and relationships. Let me demonstrate why abstraction is challenging through an example. I imagine we're playing a game with 4 distinct playing cards. Back colors are either red or black. I arrange them on the table, 2 face down, 2 face up. The face-down cards have different color backs, red or black, while the face-up show 3 and queen. The question: to disprove all red-backed cards are number cards. Which card should we flip? Most would check the red-backed card, but few realize the queen matters too. If red-backed, it disproves the rule. This is psychologist Wayson's selection task. Few succeed, but it doesn't mean we're bad at logic. And presented differently with same logic structure, people perform much better. Consider this alternative. At a bar party with underage drinking prohibited, you're checking 4 youths. 1 drinking alcohol, 1 with lemon juice, 2 empty glasses, 1 adult, 1 minor. You can check IDs or alcohol. Who should you check? Obviously, the drinker and the minor. Adults not drinking aren't violating rules. These two problems share identical logical structures, yet people find the bar scenario easier than the card problem. This shows our weakness isn't logical reasoning, but understanding abstract representations. In the house metaphor, creating blueprints equals understanding problems, while implementing plans equals building mathematical models. Completing the house represents successful mathematical modeling. From this point, the original problem's context becomes irrelevant. The efficiency gap between mathematicians and laypeople mainly emerges during blueprint creation. Mathematical work centers on abstraction, which itself has multiple tiers. The lowest tier understands only tangible, observable phenomena. The second tier involves things not immediately present, like chimpanzees searching for hidden bananas, showing second-tier abstraction. The third tier comprehends never-seen conceptual entities, such as imagining unicorns from descriptions. The fourth tier, mathematics domain, conceives formless concepts like numbers. How did humans develop this fourth-tier abstraction? This connects fundamentally with language acquisition. Having discussed mathematics, let's explore language acquisition. How do we master language? Understanding this faces multiple challenges. We can't interview infants about their language development. Native language acquisition remains elusive to direct observation. Current theories exist in constant flux, some rejected, others modified. The imitation theory, children mimic speech, fails to explain novel sentence creation. Other theories propose layered language structures. Children master basics before complex syntax. This mistakenly equates native acquisition with second language learning, assuming language develops like constructing buildings from foundation up. These theories have flaws because infants often speak grammatically correct sentences before understanding grammar rules, even correcting others' mistakes. Babbling differs fundamentally from later language learning processes. Despite flawed theories, one phenomenon remains evident. Between ages 2 to 3, children suddenly transition from baby talk like car or mama to grammatical sentences like the house is big or I'm hungry. Children across languages show remarkable similarity in initial sentence structures. Universal subject-verb construction, noun followed by verb. Examples like I angry or doggy go appear as first sentences in nearly all languages. American linguist Noam Chomsky first discovered and investigated this phenomenon. He proposed grammar structures are biological instincts hardwired at birth. This explains linguistic unity beneath surface diversity. The author agrees language isn't learned but inherent, like breathing. He views language as instinct requiring no training. Born to speak theory raises questions. How did language evolve genetically? How does instinct enable acquisition? Answering this parallels explaining bipedal evolution, seemingly simple but actually complex. Intelligence was evolutionarily disadvantaged. Stone tools and teamwork couldn't compete with natural disasters initially. Yet intelligence ultimately ensured ancestral survival and reproduction. Gradually, intelligence became evolutionary advantage through prolonged development. Between 200,000 to 75,000 years ago, crucial brain restructuring made intelligence humanity's ultimate weapon. Modern science remains uncertain about this sudden neurological transformation's origins. In evolutionary timelines measured in millions of years, this ability emerged within mere millennia. This crucial ability isn't language or mathematics itself, but rather abstract thinking, specifically fourth-tier abstraction we discussed. Its importance? In essence, it's the foundation of all human intelligence. The author takes this further. He identifies a special abstract ability more fundamental than others, dubbed offline thinking. In the house metaphor, mathematicians detach from reality to enter abstract mental spaces. This process exemplifies offline thinking. Defining offline thinking proves challenging. The author analogizes. Reacting to stimuli is primary brain function. Most organisms share this basic capability. Now imagine the secondary brain attached to the first, blind to external reality, processing filtered information from the primary brain. Here's how these two brains interact. When music moves you emotionally, that's the primary brain reacting. The secondary brain observes silently during this experience. Later, similar emotions arise viewing a painting. Then boredom strikes at the ice rink next door. When choosing between track meet or book club later, you intuitively prefer the book club, despite never attending either. This knowledge of unknown options comes from the secondary brain's ability to abstract patterns from primary experiences. With only the primary brain, such predictions would be impossible. This demonstrates the secondary brain's vital role in abstract reasoning. He observes the primary brain's processing of those three scenarios, integrating information to form new knowledge. Without direct experience, you connect reading preference through art appreciation, cultural interests, and existing associations, ultimately choosing book club. Your book club preference stems not from experience, but from synthesizing past patterns. The secondary brain enables contemplating abstract concepts beyond immediate reality and acquiring new knowledge through this process. This metaphor might sound like Pixar's Inside Out. Though I mentioned second brain, humans don't physically have such an organ. It represents the cognitive capacity for offline thinking, the brain's ability to create hypothetical scenarios and relationships. Returning to our question, how did humans evolve innate language ability? The answer likely lies in offline thinking. First, as concrete neurological function. Modern neuroscience is unraveling its biological basis. Second, as primary mechanism for learning unknowns, including language acquisition. Offline thinking bridges biological instinct and cultural language differences. Current understanding remains limited but evolving. We can posit abstract thinking fuels language, while language expresses abstraction. Now to part 3. The author proposes mathematics resembles casual conversation, a less accepted view. If language is thought's child, math and chat are siblings, both utilizing linguistic capacity. Exactly, that's the gossip in the book's title, what we call casual chit-chat in Chinese. Casual chat means saying whatever comes to mind without worrying about correctness or usefulness. It's the most natural form of human interaction. In relaxed settings, our speech mirrors abstract thinking's true nature. The author shares this case study. In Brazil, psychologists tested third graders' arithmetic skills. Despite simple three-digit problems, average scores were shockingly low, 1,400 out of 1,000. Yet researchers found these children excelled at market calculations. When a customer paid 200 yuan for 35 yuan goods, the child quickly gave 165 yuan change. Researchers recorded his self-talk. If it's 30, then 70, but it's 35, so 65 and change. 165 yuan. The child's method aligned with classroom teaching, yet produced correct results. Why then did he fail 2035 in exams? Is this child a victim of testing systems? No. Like the card game analogy, the issue lies in question comprehension, not calculation. This mirrors conversational dynamics. Social butterflies may struggle with writing or public speaking, despite conversational ease. Different communication modes demand distinct skills, though all use language. Public speaking like math, requires training, yet some master it effortlessly. To these naturals, public speaking or math feel like casual chat. How to achieve such ease? The author's answer: treat them like casual conversation. You might think, that's nonsense. I can't just magically make it feel casual. After all, skill mastery requires practice. How can I start casually? The author argues, efficiency-driven drills don't improve mathematical thinking. They neglect advanced abstraction. Learning should be enjoyable. Mathematics remains challenging to teach effectively in modern schools. Many blame teacher quality or student IQ for math struggles. The author disagrees. The problem lies in schools failing to provide meaningful mathematical motivations, turning classes into athletic drills. Real-life math applications abound. Designing movie rating systems, estimating distances with trigonometry. Even video game weapon loadouts involve resource allocation problems. People avoid math not from fear of logic, but because tedious exercises confine it to classrooms. Take movie ratings. Suppose I love a film my friend hates, sparking debate. We argue endlessly about its merits. Since films have pros and cons, we seek fair judgment systems. This need birthed review aggregators like Metacritic and Rotten Tomatoes. Metacritic calculates average scores, 0 to 100 scale, from critic reviews. Rotten Tomatoes classifies reviews as fresh or rotten, showing the fresh percentage, tomatometer. Both follow more positives equal higher scores principle. When reviews aren't unanimous, these sites show diverging opinions. Imagine midterm exams. One class of 50 students all scored 50s, another class with 30 students and 40s and 20 and 90s averaging 60. Metacritic would favor the higher average class, while Rotten Tomatoes amplifies passing rates, deeming the second class inferior. Math doesn't judge methods, just shows different fairness interpretations. Metacritic preserves more granular data, but subjective reviews don't necessarily benefit from precise scoring. This shows math's role extends beyond labs into daily contexts like film criticism. Mathematical approaches clarify disagreements in movie evaluations. Regular review readers understand both their and others' valid perspectives. Treating reviews like athletic training reduces ratings to cold statistics. Life's problems can be mathematized. Conversely, approach math problems like real-life puzzles. Math learning happens through application. Educators must abandon the flawed ideal that everyone should learn mathematics. The true educational goal: everyone should solve problems like mathematicians do. After presenting these educational insights, the book concludes, recapping 3 core questions. First, what is mathematics? What do mathematicians contemplate? Mathematics is our interface with abstract reality. Mathematicians decode pure abstractions. Second, what is language? How does language ability emerge? Language is evolutionary serendipity, enabling abstract thought. Third, what connects math and conversation? Both are manifestations of abstract cognition. To understanding this book, may we shed mathematical prejudices and find math as approachable as casual chat. If we treat mathematics like conversation, focusing not on problem-solving tricks, you'll discover its inherent charm. That concludes our exploration of mathematics as conversation. Find episode notes below. Until next time with another great book.